In this video, I'll talk about the controllability for linear time invariant system. Last time we talked about the controllability for linear time invariant system. Specifically, we talk about the definition of a controllability for a linear time invariant system. We talk about three conditions that can guarantee the controllability of linear time invariant system. And last, we talk about how can I find a control input that can indeed drives the linear time invariant system from the initial state x0 to the final state xf within a finite period of time. In this lecture, we'll talk about the same procedure, the same three-step dimension for the linear time invariant system. Now let's start with the definition. So this definition says a linear time invariant system given this form, this is a standard linear time invariant system, is controllable if for any x0, so this x0 is an initial state, okay, there exists input ut, so ut basically is sort of given by a function of t, so this initial time, let's say initial time is 0, so initial time is 0, so you're gonna initial time 0 and this defines from 0 to some tf, for example. This defines my input. And the input will transfer my system from the state x0 to state xf in the final time. Okay, for example, if my linear time invariant system starts with some state x0, and if it's controllable, if I can, for any xf, finite state xf, I can always find a control input. Of course, this control input associated with xf it can be different for different xf, such that I can drive my state of the linear time invariant system from this x0 to xf. Of course, you could find a different use of t, u to the t, and this will drive also to xf, which is fine. At least I can find a one. Then the system is controllable. So this definition is very similar to the linear time invariant system. Now let's take a look at what is the condition that can guarantee that this system is controllable. Okay, so for the linear time invariant system, we do have three different conditions. Okay, for the linear time invariant system, we do not have the second and third condition. We only have the first condition. Okay, it's about a rank of a matrix. So the condition to guarantee the linear time invariant system is controllable is one, the rank of the matrix W T0 to Tf is equal to n. Now let me explain what is this each component. So first of all, what is n? So n is the dimension of a state, meaning that if f xt is x1t, x2t, and x3t, so I have three states, so my n is 3. If you more straight, you have the dimension will be higher. So the dimension of state is the number, the n is basically the number of states you have. The wt0tf is computed in this form. It is the integration of something over time t0 and time tf. Okay, so the function is determined by phi tf t tau. Now this is the transition matrix. So I talk about linear time invariant system. This is a transition matrix, basically from time tau to tf. Okay, and this b tau is actually given over here, and this is b tau transpose, and this is phi tf tau transpose. So essentially you can see this is a transition matrix, this is time b tau, and this part is just the transpose of the product of these two. Because when you do a transpose, b tau comes first, b tau transpose comes first, and the phi tau tf tau will come the second. So the W is just nothing but integration of a set of matrix products and integrate that over the variable tau from t0 to tf. So that's what W is. And here this rank has to be equal to n, and for is, remember, don't pay attention to here, for any t0 and tf, this has to be invertible. Okay, this is a condition for the controllability. Okay, so here we're going to take a look at a few examples how we can check or verify if a linear time invariant system is controllable or not. The first example is given by x dot t is t plus 1 times ut. So here we have just say one-dimensional one. I only have one, x is one state, okay? And t plus 1 times ut, I only have one input is use of t. Is this controllable? Here we couldn't, well, of course, if we could, we can also use the second method, this condition right here. But this is really easy to figure out because I can use a definition. Because the problem is I want to drive this one to any state x0 to any state xf. Assuming that I'm starting from initial state x0, now I want to drive this one to xf. Now if this is my system, right? So you can naturally think about this one, my t plus 1 times ut is a new control input. Because I absorb this t plus 1 into my ut. So I want to design my utility, for example. I let this one to be just utility. Now what utility should I design to drive my x0 to xf? Well, one way to do that is I can let utility is just xf minus 0, right? So my tf is just equal to 1, right? If you do that one, if you do the integration, you will get, after 1 second, for example, you will drive the system from x0 in 1 step, 1 second, if I consider this is a second, or 1 unit. You will move from x0 to xf. So apparently this is controllable. Yes, it's controllable. Now let's take a look at the second example. So in the second example, we have two states. One is x1 dot t, one is x2 t. So both x1 dot t and x2 dot t, they are equal to t plus 1 times ut. So they are the same as the previous one. The only difference is now this guy controls two different states. So now, of course, I have given any new state x0. So this one means it's x1 0, x2 0 new state. I want to drive this one to xf, which means I'm driving this x1f, tf, for example, x2, tf. For some final state tf, the standard time tf. So let's say right over here, if I want to start with just start from 0 0, okay. I want to drive this one to 1 or 2, okay. Is that feasible? So according to what I said before, yeah, we can drive. If I want to drive the first state from 0 to 1, for the first state, I can design my t plus 1, use of t to be 1, and then my tf is also 1. Now I'm done. Unfortunately, at the same time, I want to drive 0 from x2 to 0 to from x2 from 0 to 2. Now enter the same input t plus 1 and ut equal to 1. If tf is 1, I can only drive my x2t to 1 at tf equal to 1. So I cannot drive this one to 2 unless I set the time tf is 2. However, if I set tf to 2, my first one will drive my state to 2 as well. Which means the main problem is these two are the same. These two are the same. Which means it's very hard, it's not possible for us to design any control because the change of x1, x2 will be the same. Which means if this is my x1, x2, this is the initial value x1, 0. This is the initial x2, 0. The change will be parallel, sort of parallel. Will be parallel. So I can only change the difference. The difference will not be the same. It will be the same. I can only change one of them. I cannot change both of them randomly because this is not a controllable. There's no. Okay. So this is basically from the definition that we can see if it's controllable or not. So now I'm going to take a look at one example that we can use the condition mentioned over here to check if system is a linear time variant system is controllable or not. Okay, the example given here is given by x dot t, which is 1002 times xt plus ET and E2t times UT. Okay, so this is linear time variance system because here this is my AT. Of course, AT is a constant, but my BT is time dependent. So this is linear time variance system. Okay, so how can I check if the system is controllable or not? Okay, so I have to use the condition over here, which is integrate from T0 to TF, phi TF tau B tau transpose phi tau TF tau D tau. So before I can compute the W matrix, that's the final goal, and I'm trying to figure out the rank, its rank. Now I have to figure out what is the transition matrix over here. Okay, because this is a diagonal, the A matrix A is a diagonal matrix, so its transition matrix is simple, relatively simple. So the transition matrix is just because this diagonal matrix, its transition matrix is just equal to e to the exponential of tau to t, and this is well how you put it. If you have 1 over here, you just put a 1 over here. If you have t, for example, you just change your t to sigma. You change the c to sigma because this is what you integrate over. And of course, you can have t squared. If t squared, you just change it to t squared. Okay. Then you integrate it over sigma. Okay. And then here the off diagonal are 0. And the second one is follow the same rule. You do the exponential of the integration from tau to t. So this is t, this is tau. Okay, the same. And then you put whatever you have over here. You just have to change whatever function of t to whatever function of sigma, and you do integrate that over sigma. Okay. If you do that one, if you do the integration for the first one, is just exponential. The integration of 1 is just a sigma. Sigma evaluate the t and the tau, give us t minus tau. This will be 0 again. This is 0 again. This is e to the 2 times. This is just 2 sigma. Evaluate the t and the tau. This gives us 2 times t minus tau. Now we can calculate what is my. Now before calculating this W matrix over here, so let's figure out what is the product of these two. Okay, so it's phi TF tau times B tau. Okay, so phi TF tau B tau. Now phi TF is I just change everything from T to TF. So which means what I do get over here is I have e to the TF minus tau 0 and 0 e to TF minus tau. Okay, this is what I have so far. Okay, now let's take a look at the time b tau. So b tau is here. B tau is e tau e2 tau. Okay, basically you have to change it to tau. Okay, this is e tau e2 tau. Okay, which is okay. If I calculate the product, is this guy times this guy, so it's e TF minus tau times e tau. And this is, second one is E2TF minus tau times E2 tau. So if you do this computation, this negative tau and tau will cancel out. So I have ETF, this will be E2TF. So this is my product of these two. Now we are ready to compute the integration of the product. Okay, the integration will be just integration from T0 TF. Now I just have this guy, time is transpose. This guy will be just ETF, E2TF times transpose, just E2F and E2TF and d sub tau. Okay, make sure, yeah, the d sub tau. Because this is not a function of tau, so I can move the outside. Just integration. This is the we can calculate the product. The product of this guy will be just e to the TF, 2TF, e to the 3TF, and e to the 3TF, and e to the 4TF. So that's the product of this two. So this is a 2 by 1 times 1 by 2, so you have 2 by 2, okay? So integration T0TF d tau. So you say this as a 1, basically, okay? So this becomes E2TF, E3TF, E3TF, E4TF. This will be just one integral 1 with just tau evaluate the T0 and TF. so which is just TF minus T0. Okay, now we are done. So we are now ready to check the determinant. So I just check the determinant of W according to the condition I mentioned over here. Is a determinant. The rank of this guy has to be n, which means a full rank. Now, which means the determinant has to be non-zero. Okay. T0 and TF is the determinant of this guy is E2TF, E3TF, E3TF, E4TF. Okay, now this constant I can put it outside, time TF minus T0. The determinant of this guy is computed by the product of diagonal entries, which is E2TF times E4TF minus E3TF times E3TF. Then I times this TF minus T0. Now this guy is just 0, right? Because this is E6TF, this 6TF just 0. 0 times this guy is also 0. So determine this guy means this is not invertible, which means a rank, the W, T0 and TF is less than n, which means not controllable. Okay, so this is how we use the condition to verify if a linear time variance system is controllable or not. Okay, now let's go to the last question is, if I give a linear time variance system a general form, this one, and give an initial condition x0 at time 0, my question is, can we find a ut? Since if it's controllable, they say if controllable, can we find some ut from t from 0 to tf such that my xtf will be indeed the final state I want to reach? Okay, xtf. Now the answer to this question is similar to the previous, to the linear time invariant system. The ut is given by negative beta transpose time phi tft. So this is a transition matrix evaluated at time t from time t to time tf, and this w inverse 0 tf. So w 0 tf is given by this over here. Okay, you just have t0 t not 0. Okay, just do the integrations. Of course, here we have inverse of that. Okay, don't forget this inverse, and time phi tf0 time x0 minus xtf. So this is the control input that will drive my state from x0 to xtf. Okay, let's see, the initial state is x0. Okay, so why is that the case? Okay, now we can calculate this one, the output based on the input based ut, to see if the xtf will be just xf. That's where the way how we can verify. Now this one is a solution for the linear time variance system. Okay, xt is phi t0 x0 plus integration from 0 to t phi t tau time b tau time u tau, and integrate over d tau. That's the solution to linear time variance system. Okay, so to verify that, we just have to check when t is equal to tf to verify if this indeed equal to xf. Okay, so if I let xtf replace t by tf, so t by tf for all t, so replace t by tf, this t by tf, this t by tf, and tau we don't keep it unchanged, and that's it. Okay, so xtf will be phi tf0 times x0. Okay, then this one will be integrated from 0 to tf, and phi tf tau we replace t by tf, b tau and u tau. U tau is we change every here ut by tau. Okay, so we have to change tau is an unchanged, so u tau ut. Okay, we have to change this one to negative b tau. That's unchanged. I have to change the t to tau. I believe this has to be bt. Let's note here bt. Okay, you change the t to tau, negative b tau. Phi tf, you change the t to tau. This one w0 tf, w0. Let's look at this one, w0 tf, w0 tf, 0 to tf, and integrate over tau. This that you don't have tau here anymore. So this is just it's related to tf basically, 0 to tf. So it's related to tf. Okay, So basically here you just have t is a function of tf, so we don't have to replace anything here. Also phi tf 0x0 minus xf, so this is also not a function of tau. Okay, we just keep the same. After we do that, we just, okay, first of all we do move this negative to the front. Okay, so this is we keep the first term unchanged, phi tf 0x0, and move the negative to the front. Inside here will be integrate from 0 to tf. This will be unchanged, this will be unchanged, and this is b tau transpose. This is phi t tau tf tau. Now we can move this one to front. That's because this whole thing over here not a function of tau, so we can move it outside. Integrate, you can see that it's constant. You can move it to the right hand. Don't move to the left hand side because this is a matrix. You cannot move to the front. So keep to the right side. Now interesting over here, if you look at this one, okay, this one, what's the integration? The integration is exactly this is phi tf tau b tau transpose and phi tf tau transpose. If you look at this w that we defined over here, it's the same form. The only difference is I start from 0, not from t0, the ending at tf. So it is exactly w0 tf. Okay, now here we have an inverse of it. So we can just cancel these terms and get an identity, which means I get rid of the whole bunch of stuff. So what I end up having is phi tf 0 x0 minus, don't forget the minus, phi tf 0, this one has to x0, forgot x0, minus xf over here. If you do cancel, if you move the negative inside, you get phi minus phi, so it's negative 0, and the minus and minus get positive, so this is xf. Okay, so that's why this input ut will drive the defined from interval from 0 to tf will guarantee that my xtf will be xf for this linear time invariance system.